Welcome to today's webinar, announcing AWS Step Functions. Our presenters today are Andy Katz and Tim Bray. Andy is a Senior Product Manager for AWS, and Tim is a Senior Principal Engineer for AWS. Today with us we also have Juancho, Aaron, and Tara serving as our webinar moderators who will be engaging with you and answering your questions throughout the presentation while Andy and Tim present. Andy, Tim, welcome. The floor is now yours.
Thank you. Well, good afternoon, everybody. This is Andy, and I'll be presenting today. Tim is with me as well. What we'd like to do is try and make this session today a bit interactive. So we'll be showing you slides, we'll be showing you demos, and we'll also be trying to answer your questions both during the presentation as well as have a block of time for questions and answers after the presentation. So as you think of them, fire away, and we'll take ones that we can during the talk and clean up the rest at the end. Today we're talking about a new service that was announced on December 1st at reInvent in Werner Vogel's keynote speech called AWS Step Functions. So we'll talk a little bit about why this service was created. So there's a trend in application development that's sort of mirroring how we think about companies. So we're moving applications from a monolithic scale to a human scale. And if you think about a company is this big entity that does one thing, but it's made up of departments. And those departments are things like finance or HR or R&D. But within those departments are people, and people do tasks. And so software applications are starting to mirror this. We're going from these ideas of monolithic packages that do things like enterprise resource planning to packages that focus on one area of specialization, sort of at the scale of a department, like finance or manufacturing. And these would be the form of like microservices. But even within microservices, we're starting to decompose them into smaller functions. So things that you do, say, within a sales department. And this is moving from monoliths to microservices to functions. When you get to functions, it creates some challenges. Now, there's good reasons why we move in this direction, because it makes our applications more resilient, more durable, more resilient under failure. You don't have weak links in the system. You have independent failure points, and they're easier to scale. But they come with challenges. And one of the challenges they come with is keeping track of state. We'll talk about that in a minute. Now, when we move down that spectrum from monoliths to microservices to functions, we move into the landscape of a serverless application. And many of you are already building serverless applications. Some of you are thinking about doing it in the next year or beyond. And so what is a modern serverless app? Well, it begins with a function in the cloud. And in our case, it's an AWS Lambda function. But Lambda functions, to do simple things, they last about 5 minutes. But when you build an application, you may want more than one. And when you have more than one Lambda function, they may want to talk to each other. And so you need some way for Lambda functions to communicate. Here we go. And of course, more Lambda functions want to communicate. And many kinds of communication. So they may send different messages to each other in different directions at different points in time. Those Lambda functions may also find themselves talking to, for example, a database. Or they may be putting things on a queue. The slides are a little slow to update. There they go. And beyond activities inside the cloud, there's still a lot of on-premises servers that we need to talk to as well. And so your Lambda functions, in addition to talking to databases and queues and each other, may also be talking to servers on-premises. Here we go. But if we take away all the resources, the Lambda functions, the queues, the servers and the databases, what we have the communication paths between all of them. And there are different kinds of communication paths. Sometimes it's do this, sometimes it's can you do this in parallel, sometimes it's do this, then that. How do we think about coordinating all these different independent activities? And that's what Step Functions is addressing. So there's a lot of different things you think about when you're building a serverless application. You may want to do things, for example, like sequence functions. You may want to run your functions in parallel. You may want to select functions based on data. You may want to retry functions. You may want to, when error messages come in, have try-catch finally patterns so that you go different places with different errors. And sometimes you have code that runs longer than the lifespan of a Lambda function. You have code that runs for hours, and you want a way to manage a process that includes steps that take hours or even days or even weeks. So you want a way to coordinate all these things. And so there's a set of must-haves in coordinating functions. And there are 5. The 5 are, you want to be able to scale out easily. You want to keep track of state. You want to be able to deal with errors and time.
So this is Tim talking, and all of these are more or less glaringly obvious, but I think we want to focus in a little bit on the last 2 in the list here, because the things we want to do, like such as run functions in order, are easy to talk about, they're easy to understand, so they should be easy to implement. And the last thing on that list was an audit trail, and there's a variety of different ways to coordinate things in the cloud, but if you're not careful, you can end up with your log all over the place. So we think it's a really important feature that the log be in one place so you can track what happened and debug, analyze, build, do all those things you need to do.
And so this is why we created AWS Step Functions. And the intent is to make it easy to do all this coordination of components of your applications in the form of visual workflows. Let's talk about what that means. So as Tim mentioned, one of the key things is you'd like to be productive. You want to make it easy to connect and coordinate these microservices and functions to quickly create apps. We'll show you how that's done. You want to be agile. You want to be able to find problems faster through that audit log. You also want to be able to adapt your application and make it change as needed quickly. And ultimately, you want it to be resilient. So you want to be able to do this at scale in the cloud and durable under failure conditions that are often not in your control. So first question we'll ask is, how does it work? And so we'll talk about the application lifecycle in AWS Step Functions. And there are essentially 3 steps. First, you'll define your application workflow in the form of a state machine. These state machines are defined declaratively using a JSON syntax in a language we call Amazon States language. Those JSON documents can be visualized in the AWS Step Functions console. What you see here in the middle of the figure is a state machine representation of a JSON document on the left. So you can see what your state machine looks like, but you can also use that to monitor your executions in the console. In this case, we give you visual feedback by changing the color of the states depending on what's going on. We turn them blue when they're work in progress, they're green when they pass through successfully, they turn red when there's a failure, they turn yellow when there's a retry. And we'll go in depth on the monitoring executions on the console and other sources in a moment. First, we'll take a look at how we define our state machines. There we go. So the JSON you see on the left is defining the state machine on the right. This is a canonical Hello World example. It's a very simple one-state state machine. You can see you can begin your state machines with comments, so you can annotate what you're doing in a state machine. You tell it where to start, in this case a Hello World state, and then we define states. In this case, the Hello World state again, defining what type of state it is, what resources it needs, and whether it's the last state in the state machine or there's a next state to go to. And this JSON on the left defines the state machine you see on the right. Now we're going to talk today a lot about individual state machines, but I think it's important to realize that we can launch more than one state machine at a time, and in fact support up to 1 million concurrent executions per account. So we'll look at individual state machines and individual executions, but bear in mind this is a service that allows you to launch many, many state machines at problems, many different kinds concurrently executing. So we'll take a look next at the console. And what can you learn about your state machines from the console today? So on the upper left, what you see is a graph of the state machine. And again, we talked about how that gives you visual information about the execution of your state machine. You can also look at the tab that says graph or code. When it's on the graph, you see the graph on display. If you click code, you'll actually see the underlying JSON that defines that state machine. And so that lets you toggle back and forth between a visual representation and a text representation of the state machine. If you go to the upper right part of the console, you can see 2 windows. One is execution details, the other is step details. Inside execution details, you get information about your state machine execution. You can find out if it's succeeded or failed, or if it's in progress. You can get the ID of the state machine, both the state machine by type and the specific execution. These are in the form of ARNs. These are Amazon resource numbers that are basically labels and the timestamp of when you started and ended your execution. The other tabs you see, input and output, let you look at the JSON documents you passed into the state machine when you started execution and the output the state machine produced upon completion of its execution, again in the form of JSON key value pairs. The tab at the bottom says step details. If we open that up, you'd be able to take a look at individual states in the state machine, what input they received from the states preceding, and what output they gave to the states that followed. And then at the bottom of the console is a full audit trail, as Tim mentioned, showing you every step that was executed during the execution of a state machine. And it gives you details about each step, including things like when did I enter that state, when did I schedule my Lambda function, when did it start, when did it finish, and when did I go to the next state, including retries and error messages that come along the way. In addition to monitoring executions from the console, we also give you a couple other ways. You can send this information to CloudTrail, or you can monitor executions from CloudWatch. So with CloudWatch, we can do things like Lambda functions we call per minute. In this case, we're looking at the blue curve showing that in the state machine execution, we're launching about 70 Lambda functions per minute. Or we can look at the average duration of those Lambda functions. And so in this case, the orange curve is showing us Lambda function durations averaging between 200 and 300 milliseconds. And so this information you can get during execution of your state machines from CloudWatch today. So let's talk about different things you may want to do. So suppose you want to sequence functions. Let's talk about some examples of customers of ours have had. So if you want to sequence functions, we have a customer called Food Panda. Food Panda is a delivery service that pairs restaurants with customers around the world in multiple countries, and they essentially need to dispatch delivery to different drivers that are available in different regions they deliver to. And they need a mechanism to do this. And so,
Now, Tim speaking here, if you think about what Food Panda does, as a subset of solving their problem, they have to solve the traveling salesman problem, which is NP complete. So we should take our hat off to them, because obviously they're smart.
so Food Panda has a state machine that looks something like this. Food Panda has an order, and they want to match it with vehicles that deliver to the zone the customer's in. So the first thing your state machine does is say, what vehicles are available now? So they ask, first state, load available vehicles. Once they have that list of available vehicles, they're going to want to run an assignment algorithm and pair the orders with the vehicles that can go to the zones they want to deliver to. Once they've done the assignment, they want to dispatch those vehicles by notifying the drivers where to pick up the food and where to take it to. And if they succeed in contacting the driver, they'll tell the customer. If they can't get a hold of that driver, then they have to reassign that food to another driver and send it back to the beginning of the state machine. And so what you're seeing here is that state machine that includes the ability to make sure that things occur in a particular sequence, and when there are problems, like a driver's unavailable, it reassigns that work to the beginning of the state machine to try again and find a different driver to succeed in delivering that food. Now we're going to take a closer look at two states to drive a demo, which is doing things in order. In this case, we're going to take a closer look at running the assignment algorithm and dispatching the vehicle. And so if we take those two pieces and zoom in on them, we'll make a simple state machine that just has those two states. And it looks something like this. So the code you see in the bottom says, let's sequence a couple of functions like Food Panda, and we'll start with run the assignment algorithm, and then we'll dispatch the vehicle. But we don't want to do these things out of order, because if we try and dispatch orders to a vehicle that have not been properly paired, we have a mess on our hands. So the state machine starts at run assignment algorithm. The first state calls it resource, in this case a Lambda function. And in our particular example, we're going to use a Lambda function that does something a little bit different. Tim will talk about in a moment. We've written some code that will post messages to Twitter, and what we want to do is post these messages in order. Code is going to come up, and it looks something like this.
So this is Tim. I'll talk through this. I hope you folks can read Node.js code. All this function really does is tweet to prove that it ran. We didn't want to run one of Food Panda's own Lambdas because they're not that interesting unless you care about meal delivery. If you look, what it does is it goes and pops a variable called list off the front of the input event input, which it expects to have a field called input list, and puts that in the variable text to tweet. And then if you go down 2 or 3 lines, it actually goes and tweets that text, pushes it to Twitter, and if everything was okay, then it does a callback and passes whatever was left in the list off to the next state. So all it does is pop something off the list, tweet it, and then pass along to the next state.
So with that, we'll take a quick look at a demo of how this works in action.
So if we could switch over to my screen. Excellent. So this is a look at the actual state machines console. And I have a few state machines in here. So let's look at the Food Panda state machine. You can see some history of previous executions. And let's actually just start a new execution there. And it will ask me for the JSON that goes into the top level. So remember, it wanted a field called input list, and it wanted the value of that field to be a list of strings. So I'll just say, hello there, webinar. And I noticed the most recent question came from somebody named Sanjay. So we'll put him in there as well. And let's just run that state machine. So it shows you the first box in blue because that's currently running. Now, this console's a little bit behind. It's just 2 lambdas. So in fact, both of them will have run by now. So as soon as the console updates, there they are. You can see they both turned green because they've run. If I scroll down a little bit here, you can see a detailed audit trail of everything that happened. The type is a little bit small, but you can see, it started the state machine, it entered the task state, it scheduled a Lambda function, it started the Lambda function succeeded, it exited the next Lambda function. So whatever happens in the course of the state machine, you get a nice audit trail in one place. There are APIs to get at it, of course, and they are thoroughly gruppable. So you can go and see what's happened. Now let's drill down a little bit. I'm going to click on that first state called run assignment algorithm, and then I'm going to see what was the input to that state. And as soon as the screen refreshes, you will see that it was that text, that JSON text that I typed in. Screen here is not very sensitive to single-page application-style JavaScript refreshes. On my screen, I see that it's a JSON object with a field called input list, whose value was hello there webinar, and howdy Sanjay. And, oh, there it is, finally. And the output was the same list with howdy Sanjay. Oh, there it is, with this howdy, with only the howdy Sanjay part left on it. And I want to take a minute and talk about this. The notion of control moving through the state machine is really easy to understand. It turns out that the actual transient state of your application is captured in these blobs of JSON that move from state to state to state. And well, we have all sorts of tools for manipulating that and dealing with that. And the core thing that the service actually does is track that data as it moves through, persist it reliably, and make sure that no matter what happens, the states in your machine get executed in order. One thing I should say is that this is not entirely brand new software. A prior version of this service has been running for a while, and internally at Amazon, we are running roughly 1 billion state machines a week. So this stuff is well shaken down and solid. With that, I'll toss it back to Andy to talk about some more things you can do with state machines.
Yeah. So another example is you may want to select functions based on data. And so an example of this is a customer of ours called The Take. The Take is a very interesting business. What they allow you to do is discover the products that you see in your favorite TV shows and movies. And so what they keep track of is what the actors are wearing, maybe a pair of shoes or a watch or a different jacket or shirt. And that means they have a database. And they have a database that says, who makes the shirt, what's it cost, is it available, and who's it available from. And that database needs to be updated all the time because fashion changes, availability changes, and they want to keep their information fresh. For them, this used to be a manual process, and it just reached a point where it was unsustainable and very, very painful. And so they replaced it with a state machine. And in this case, they partner with a number of different vendors. And so they need a way to look in their database, say what is available, and then go to the correct vendor's database, look up, check to see if the price changed, check to see if the availability changed, and update their database accordingly. And so their state machine looks something like this, and it begins with a choice state. So they go in, having pulled the item from their database, saying which vendor was it? Was it vendor A, B, or C, or possibly somebody else? And based on that, they go to a Lambda function that either calls vendor A, vendor B, or vendor C's database, looks up the item, and returns it. And if they aren't able to find it, they can reflex to a screen scrape state to capture the information and then go and update their database.
So in this particular machine, the ones in the middle row, vendor A, vendor B, vendor C, and screen scrape, are Lambda functions. And we have a question from Aravind out there who asks, what are the key differences between step functions and Lambda functions? And I think this picture kind of addresses that. The big deal here is to orchestrate the Lambda functions, because it turns out that most interesting applications don't have just one entry point, one module, one thing they do. They tend to be made up of lots of different functions, and in the serverless space, you often want to orchestrate those. You want to say, run this function, then that function. Run these 4 functions in parallel, that kind of thing. Now, it turns out that people are already doing those things, and they're doing ad hoc coordination code using Dynamo databases or queues, or they're chaining from function to function, all sorts of interesting stuff like that. But they're having to do it themselves, and it's more work than it should be, and they get a problem sometimes in that you can get an impedance mismatch between Lambda, which scales more or less infinitely in databases, which don't, and there's another problem in that when you orchestrate your own functions, you may end up losing that nice audit trail. So that's the idea here, is to provide the coordination functions and the audit trail. So thanks for that, Aravind.
Now there's another question from Sanjay asking about how to distinguish between state and transitions. So we'll take a look at the take state machine, because this is a good example of that. The states are what you see in the dashed outline boxes. Those are individual states. So I'm in a choice state, that's a state. I'm in vendor A's Lambda function, task state, that's a state. The state transitions are these arcs or arrows connecting the states. And the idea is that each of these states does a piece of work, either a task or makes a choice or waits a little bit. And so they're passed stateful information into the state, work is done, the results are passed out in the form of state, and essentially that Lambda function remains stateless. It's called, it completes its work, it goes away. So that's how you differentiate between state and state transitions.
Boy, we're getting lots and lots of good questions. Aaron, if you could assign that one to me. Manish, let's do one more and we'll go back to the presentation. Manish asks if there's support for passing the output of one function into the input of the next. And yes, 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 yes. That's the crucial thing that this thing does. By default, it captures the output of each state and passes it as input to the next. Now, it turns out that it's not quite that simple, and there's some ways you can fine-tune it. And we'll get to that a little later in the presentation. I think we should give the wheel back to Andy now and let him move forward.
Okay, well, let's take a look at what a choice state looks like inside the take state machine. So we'll take a look at the actual JSON code and walk you through the code that generates this state machine. So it begins with the notion, in this case we called it a choice state. So what you're seeing there is the name of this choice state is a choice state. We specify the type, so you can see we said choice as opposed to calling it a task state. And then we have an array of choices. So each choice is an individual comparison that compares a variable with a comparator criteria and where to go if that criteria is true. So in the first case, we look at the variable which calls the input that went into the state in the form of a JSON path. So product source is the key of a key value pair in the input into that particular state. And then we ask, well, it's a string. Does the string equal screen scrape? If yes, then go to the screen scrape state. If that's false, go to the next comparator. In this case, look at the same variable and say, does that string equal vendor A? If it does, then go to a state called vendor A, and so on and so forth. These comparisons can be comparisons of strings, of numerics, of booleans, and timestamps. And we can have comparisons of equal to, greater than, less than, equal to, or less than, and equal to or greater than as comparators, as well as and, not, and or compositions of logic. And so this way you can create a rich case statement that lets you go to different states in your state machine depending on what output came from states before.
The people in the crowd who are JSON experts, if you look closely after choices, you see the square brackets. So those things are actually an array. And so to be very precise, the behavior is the service looks through the array of choices until it finds one that matches, and then looks for the next in there, and then moves to the appropriate state.
So sometimes functions fail, and you may want to retry them. And so if you're, for example, working with a RESTful service that you're calling, we'll jump ahead in a moment, you may want to retry if it fails, because sometimes these services are intermittent, and you'll call, they work, and then they don't work. So how does one call out a RESTful service? So within a state, for example, task state, you can ask to retry on the basis of success or failure. So the code looks something like this. So this is a different kind of state than we looked at previously. Previously we were looking at a choice state. Now we're looking at a task state. The task states are the states that do units of work. These are the states that either call a Lambda function in a serverless application, or alternately they can take activities requests from things like EC2 instances, and we'll talk about that in a minute. So if you look at this statement, what you see is we've got a resource, in this case a Lambda function, calling something called REST callout. But if it fails, we can retry. And that's the array we show below, where we say retry, and we say if the error comes back as a handled error, retry. And in this case, how many times? Max attempt says try 10 times.
Once again, if you look closely, you can see that the value of retry is an array. So you can have different clauses in there to handle lots of different error conditions. Some kind of errors you might want to retry, some you might never want to retry. I think it's not hard to imagine scenarios like that.
Now you can build upon this, because beyond retry, you can also say, well, if I terminally fail, where do I go? And this would be the pattern of try, catch, and finally. And so an example of this is another customer of ours called OutSystems. OutSystems uses this in a DevOps setting because they want to consolidate alarm systems from a variety of different microservices and separate the signal from noise. Right now they started with a very noisy system, and this allowed them to make a quiescent system where only the important alarms rose to the top of the stack. Their state machine looks substantially more complicated than ones we've shown you to date, but it actually is quite simple once you walk through it. So this is an example of a state machine that OutSystems uses in production today to sort through alarms from 4 different sources, bring them in to the state machine, and filter down 3 different paths to ultimately get to alarms that separate the alarms that matter from the alarms that don't. And so this particular state machine has 13 Lambda task states, 6 choice states, which we've highlighted here in orange, and a fail state, as well as a successful exit. And so these 4 different sources go in, and what you see highlighted in the upper right orange is the first choice state, which determines whether it's an alarm, a monitoring issue, or an alarm that's coming from a child that should escalate up to a parent alarm and then process further. Another example of this is so let's simplify it a little bit and take a look at another example where try, catch, finally is used, and this would be in management of media assets. And so in this case, I might be moving media from one storage file to another. And if I successfully migrate the media from one data store to another, I have a graceful exit. But sometimes I get interrupted halfway through my process, and so I may want to actually undo what I've done and clean up. And in this case, if I have a failure, instead of just going to failure, I can default to a different state and say go clean up. And if the cleanup is successful, I still have a graceful exit. But if the cleanup also fails, then I can flag serious breakage with an alarm and say someone has to go in and manually clean up the mess that was made.
Now, it turns out that, of course, if you're writing, whenever you're writing your Lambda code in, be it Node or Python or whatever, all those languages have try, catch, finally idioms. So you could decide that you were going to do your error handling right there inside your function. Having said that, I think this is probably better design. In an ideal world, I would like to see functions that just do one thing, one simple thing, and do them well, and leave the error handling to be done at another level.
So what does try, catch, finally look like in code? So this is an example of the graceful exit. And so here, what we're saying is we're accessing media. We've got a resource for this task state, find the media. We give it a 2-second timeout. So if it doesn't succeed in 2 seconds, it says the resource is not available, and we'll try again. And we say, well, how often? So we say retry. If there's a timeout, retry 2 more times. That's the max attempt. But each time, wait a little bit longer. That's the back-off rate. So it's normally 2 seconds on the first try, and then we extend that out to 3 seconds on the next try, and then we extend that out again to 4.5 seconds on the final try.
Actually, it turns out that in this one, it'll only retry twice. So it'll be 2 and then 3. You also may have noticed that on the previous retry state we showed you, there was no extra stuff about back off and so on. There's defaults for all this stuff, and pretty good defaults. But I suspect a lot of people would like to fine-tune it the way it's been done in this example.
Now the thing that's new in this is the catch state down below. So like retry, it's in the form of a JSON array, so there's different catch states that you can go to. In this case, there's one. We say if any error, this is a reserved error type, begins with the prefix states, we go to the cleanup state. We could also have different errors, so if it was a timeout error, go to one state, and if it's a task failure error, go to a different state. So we'll take a look at the demo next to show you an example of using retry in a state machine.
Very good. If we could switch the screen over to me. Okay, we're back to the state machines console, and here is an example of RESTful callout. And this is that same state machine that Andy just showed you a few minutes ago that just retries something 10 minutes, a maximum of 10 times. And to make this demo work, I have set up using a Lambda function that fails a lot, like more than half the time. So it doesn't actually look at the input. So let's just run this guy. And it's called out, and I don't know how well your screen will update through the webinar software, but give it a second to refresh. And oh, it worked on the first try. No fair. I'm going to run it again. We got lucky. The Lambda started, succeeded. So we got very lucky. I've seen this thing run as many as 10 times before it succeeds. But you can see it. There it is. It paints it blue because it's running. And the Lambda function started. Let's give it a minute to refresh the console. There we go. Okay, I'll manually refresh the console. Well, it looks like the demo gods are frowning sternly on me at this point. The console just isn't refreshing. Oh, well, the picture isn't refreshing, but the audit trail is. If you look down here at the audit trail, you can see that the function started, failed, started, failed, started, failed, started, failed, and is still failing over and over again. And given enough tries, since there's up to 10 retries, it will eventually turn green and succeed. And if you look at the actual state input and output, you can see that it had an exception as it went along. If we go down to the very bottom, we'll give it one more chance before we knock this demo off, and it's still failing over and over. Anyhow, never mind. Let's go back to the slides.
Oh, so we have a question from Khan asking that state machines are effectively source code. And so how do ones have multiple versions running at once, and how do you manage the application lifecycle? So a couple things on this. When you register a state machine, you're essentially registering the type of state machine, and then when you run them, you run individual executions. So you give your state machine itself a name, and then the individual executions get a different name. The service can assign a name for you, or you can choose to assign a name yourself. At this point in time, we don't support explicit version control of state machines and their executions. So a pattern we recommend customers to consider today is simply just include the version number in the name for management. So you'll discover that when you're registering state machines on the console, once you register it, you can either delete it or run it, but you can't edit it. So if you want to make changes to your state machine, we recommend keeping a copy offline for making changes and using version numbers in the name today to increment versions of your state machines as they evolve over time.
It is, however, correct to point out that they are a lot like source code, and in fact, it's just that it's a declarative JSON language as opposed to a procedural language.
Now, another question is, we've talked a lot about using Lambda functions, and we've talked a lot about serverless applications, but it's also true that AWS Step Functions supports long-running compute. So you may have code that runs for hours. You may need to gather data during an 8-hour shift in a production line in a company, and Step Function supports this as well. So in addition to being able to push tasks to Lambda functions, we'll talk about other ways of getting information. So let me get the slide to come up.
Well, while we're waiting for that slide to advance, there's a question from Nathan out there saying, how closely related are SWF and Step Functions? Now, for those of you who don't know, SWF is an AWS service, simple workflow. It's been running for a while now. And it turns out that the Step Function service actually uses an enhanced version of the SWF backend. Now, SWF had a reputation for being complex and hard to learn, and I think we should have convinced you by now that Step Functions is immensely, insanely easier. But having said that, the SWF backend is well developed and well debugged. The question was, a specific question he asked was, how about reusing existing activity code from old SWF programs? Unfortunately, we don't support the flow library. So if you were coding to the native SWF API, you're fine. You can just take that. You have to change the endpoints, but aside from that, you're good. You can just run that as an activity the way Andy's about to describe in Step Functions. And why don't I just let Andy go ahead and describe that then?
Yeah, so for those of you that are not familiar with simple workflow, we're going to talk about the two ways you can do work with Step Functions. So we talked a lot about pushing tasks to Lambda functions. And so that's shown at the bottom state of this state machine. And essentially there, it's you declare a task state, you give it the arn of a Lambda function, and what Step Functions will do is pass the input to the Lambda function for processing, and when the Lambda function returns its value, that's returned to that state as the output, and that's passed along to the state that follows. But there's another way to dispatch work in Step Functions, and that's what we call an activity. And this is analogous to Simple Workflow's activity workers for those of you that are familiar with Simple Workflow. And here, any compute instance that can reach the Step Functions API over the internet can request and receive work. And the idea is an EC2 instance or an ECS container or even an on-prem server or even your mobile phone long polls in for work. So by long poll, that means we make a connection, we hold it open for 60 seconds, and those activity workers that know how to do a particular task present an ARN that is registered with Step Functions that says, I know how to do this kind of task. And when there's an executing state machine that gets to that kind of a task, in this case it would be a task called upload a raw file, Step Functions says, is anybody polling for that kind of work right now? And if the answer is yes, it dispatches the input to that worker, says do this work and call me back when you're done. The worker acknowledges receiving the input, processes, and calls back when it's completed, and delivers the result, which Step Functions then takes and passes along to the next state in the state machine. And so the same paradigm as Simple Workflow, and as Tim was mentioning, if you've written activity workers for Simple Workflow called the native Simple Workflow API, you can move them over to Step Functions by simply changing the polling code to call the Step Functions API. There's a limitation, which is if you wrote your code using the Flow framework, then it's not as easy to modify to work with Step Functions. And that's a limitation, but that's the key difference.
Boy, are we ever getting a lot of great questions here. Way back at the beginning, Chris asked how to interact with humans to input state into a workflow. And at the moment, you'd have to use this thing, where you would have an activity that actually polls for a task, gets a task, goes and interacts with a human through one way or another, and then gets back. So that's how you would cover that base.
So taking a look at these task states again, this is an example of pushing, a push state. So in our Hello World example, it's a task type, and the resource in this case is a Lambda arn. So you can see it's got the keywords Lambda and function inside the resource, and that tells states to dispatch to the Lambda function with that name in that region. When we do the long poll and we request work, what we do is register an activity with Step Functions which is then used as the ID of the kind of work the worker knows how to do. And so this is an example of the code for a task state when we're having an activity worker pull for work. And so now the resource has the form of states activity, state being the endpoint of the step function service at AWS, and activity is the type of arm which tells the step functions in this state wait for somebody to long pull in for work and dispatch to them when they ask. So there's some interesting things we can do with an activity worker that shows up in this code. So this is an example of a task state that's going to a state's activity. We can have a timeout, which we talked about before. In this case, a full 8 hours is about 28,000 seconds, so we've got a timeout that exceeds the 8-hour shift. But we also can do something which says require that activity worker that's going to be running for a long time to let us know it's still there. Because if we have a compute task that lasts 10 days, and some of our customers do, if it fails on day 1, we'd rather know then than 10 days later. And so that's why we introduced this statement called heartbeats. And you can see here, the heartbeat second says every 2 minutes, call in and say, I'm still running.
Let me talk a little bit about this at the API level. If you're a coder and you want to make one of these activities, so the first thing you have to do is you have to register it, saying, I'm going to make an activity that does such and such a task, and that will give you an ARN. And then when you write your activity code, there's a few APIs you use. One is to call in and say, here's the ARN I know how to do. You got any of those for me? That's the long polling that Andy was talking about. Then there are APIs to call back and say, yeah, that worked, I succeeded, or alternately, sorry, I blew up. And then there's a third API, which is to call in with a heartbeat and say, hey, I'm still here, I'm still working. And you can see it in this example here. If the activity that you've dispatched to doesn't call in at least every 2 minutes, then you're going to declare a timeout and blow away. Now, there's another interesting thing in this particular state machine that you see on the screen, and that's the first state. You didn't talk about that yet, did you, the wait state there?
No, not yet.
Okay, so let's talk about that a little bit. So in this particular case, we are going to monitor some piece of equipment for an 8-hour shift, and that means we don't want to start until that shift starts. So one of the things you can put in a state machine is a wait state that says, well, wait for a while. And you can put in either an explicit number of seconds to wait for, or an explicit timestamp to wait for, or you can do the thing that they're doing here, which is to pull a field out of the input data, the shift start field, and assuming that is a timestamp, it will wait for presumably the next 8-hour shift start, and then put the whole state machine to sleep until that time comes along. Then it'll wake up and start pulling for that task and get to work.
So sometimes you don't want to do things in a linear order. Sometimes you want to run functions in parallel. And when we say functions, you should always assume we can also talk about activities. So an example of what does something in parallel look like is you're doing something like image processing. Or you're doing, in this case, an example of a customer that's interested in doing optical character recognition. And so maybe doing a bake-off between 3 different forms of OCR, as the case in this example, and you want to go with the one that gives you the highest confidence value. You could run these things sequentially, but you're spending a lot of time waiting for that compute to finish. So why not dispatch it in parallel, which is the whole point of doing things in the cloud in the first place. So how do we do that in step functions? So step functions supports, within a single state machine execution, a parallel state that allows you to fork and join tasks. So in this OCR example, the state machine looks something like this. So we tell it to start. We get the same information. It gets split across 3 different branches. There's a prep step, and then we go and compute, and then we pick the result from the 3 that come back at the end. What does the code actually look like behind these 3 branches? It looks something like this. Here we go. So in this case, the type of state is a parallel state, so we say type parallel. We tell it what's the state in the state machine that we end up at. In this case, we call it pick result. And then we define branches, and you'll see it's in the form of an array. And so it's an array of branches to go down. So the first branch starts at a state called prep1. We define what that state does, where it goes next. And after we define all the branches and the states in that branch, we'll define the second branch. We'll say start at prep2, and where does it go until it concludes? And then we'll define the next branch and say start at prep 3, and that's how we build up that state machine in a parallel state. Now we've danced around this a little bit, but there's a question about, well, where does state live during state machine executions, and how we pass it from state to state and from function to function. So the basic answer is it lives in the state machine in the JSON blocks that are passed from state to state as inputs and outputs. So let's talk about what that looks like a little bit. So raw input to a state machine, you've seen some of Tim's demos, is in the form of JSON key value pairs. So for example, it can be text or it can be numbers. As it looks, so the raw input at the top you see is examples of text and numbers. Yeah.
So in this case, we've got a Lambda function that knows how to add an array of numbers. And that's all it knows, and that's the way the Lambda function should be defined. But we've got raw input, which got a title and the numbers as one of the fields. So in that state machine specification, it's got a field called input path, and the value of that is a JSON path. You've already seen a couple of these JSON paths around in earlier examples, and that just selects that one field out. So all that the Lambda function sees as input is that array of numbers.
So then we talk about how we process that input. So there's a series of notions around that.
So while we're waiting for the next slide to show, Howard asked us, what is the typical latency between the input-output execution and the next functions? The answer on that at the moment is on the order of a second or so. This is not something that's suitable for things where you need microsecond latencies, but something on that order. Andy, why don't you skip that one and go on to the next one, because we're getting short on time here. These are the deep dive details.
Okay. Did you skip through that?
Yeah. So the next question is, we've shown how you can affect the input to your function. Let's talk about dealing with the output from the function. And as soon as the next example comes up on the screen, here it is. So in this particular, that's the same example. So we've used the input path field to send just the array 3, 4 to the Lambda function. Now let's suppose that Lambda function just emits the number 7. That's all it does, is add the numbers, and that's good design. So we've got another field called result path. And so instead of the whole output from the state just being the number 7, we actually insert that into the raw input. So the output contains everything that came in, plus a new field called sum, which is 7. Once again, you're seeing the use of a JSON path here. This is a common programming idiom. We have seen people actually have a bunch of states that build up a richer and richer field as they move along. Andy, I'm thinking that there's a huge number of really good questions there. Maybe we should just climb on board and answer some of the questions.
I think that's a good idea. Let me see.
Let's do some easy ones here. Some of these have already been answered by Aaron. Vlad, can you use Python instead of Node.js? Yes, you can do anything that you can do in a Lambda function. Diago, is there any limit on execution time? Well, the limit on execution time is 1 year right at the moment, but we think that that's actually artificial, and there's no reason a state machine couldn't run forever. However, we suspect that if a state machine's been around for a year, there is a chance that it's been forgotten, abandoned. It's a poor little orphan state machine. So that's the limit for the reason for that limit. Andy, do you see any you want to jump on? Let's see. Here's a whole slew of them. Boy, there's a lot of good questions here.
Let me wrap up with a few last items about step functions, and then we can answer more questions.
Oh, if I want the same function but with different inputs in parallel, can I define that state once and refer to it in multiple branches? You can use the same function more than once, but the states all have to be unique, and you can't have a state with the same name both in a branch and on the main line of your state machine. And if you think about it, that actually avoids a bunch of problems that we might otherwise have. Back to Andy.
Okay. So we'll just close a few things in the slides, and then we'll finish off with lots of questions. So beyond the set of questions of, are these the kinds of things you'd like to do that Step Functions allows you to do, another question is, well, where is it available? And so we'll say today it's available in 5 regions, all regions where we also have availability of Lambda functions as well as EC2 and ECS. Those regions in the US are North Virginia, Ohio, and Oregon. We also are available in Ireland in the EU and Tokyo in Asia Pacific. And so if you'd like to get started, it's easy to go into the console. You'll see a screen that looks like this. Click the blue button and you get started. So we're at amazon.com/stepfunctions. And you can choose to go either to the documentation. There are 4 items in the documentation, one of which is you can go to the developer guide. We also have an API reference. The states language specification is also available. And we have a tool on GitHub called Statelint, which is a static code validator that will let you check your JSON code before you try to register it with service. It lets you find syntactical errors very quickly. We also recommend that perhaps the easiest way to get started is simply go to the console and try it. If you go to the console, and Tim can show you an example in a moment, we've got 6 blueprints that demonstrate something we talked about today in terms of that hello world example, await state, parallel states, catch and retry, as well as choice state. And it's as simple as clicking on one of those, setting up your Lambda function, and off you go. And it might be even simple enough for Tim to show you in 1 minute what it looks like to set up a hello world example.
We could do that. Let's look at 1 or 2 more interesting questions here. There's been a few questions from a bunch of people of the form, oh, can I send a message to an SNS queue? Can I do an AWS run command? And basically, the answer to all of those questions is, well, you can do anything you can do in a Lambda function. And a Lambda function can call basically not just any AWS API, but it can call any RESTful API out in the world. So basically, the answer to all those questions is yes. So Sanjay, who has a lot of questions, has another good one. Sanjay asks, how to provide monitoring for step functions. So when you actually launch a step function, so to start with, there's console monitoring that we've been showing you. And that's useful because if something fails, it lights up in red and you can click on it and see why it failed. But from the programmatic point of view, there's an API, of course, to launch a step function. And when you launch it, what you get back is an execution ID. Because it's perfectly reasonable to run the same state machine, thousands or millions of times. But each time you run one, you get an execution ID. And then there is an API to use that execution ID to query the progress of that state machine and also to actually walk through its history, its audit trail. So yeah, all that stuff is accessible programmatically. What's this one?
We're at the end of the presentation. We're going to basically be trying to pick off as many of your questions as we can with the time remaining.
So somebody asks, could we talk again about human functions? And I think at the moment, there's no direct support for human functions. There is, however, you can do that fairly straightforwardly from an activity task. So it polls and the service hands control to it and then waits for it to finish. And that activity task can be anything. It could, in fact, be the implementation of an Alexa skill that interacts with humans through an Alexa, or almost anything else you can imagine. At the moment, there is, however, no direct support for human tasks.
So,
go on, Andy.
Well, there was a question earlier about how to explain step functions to non-technical people.
Good question.
I think that's a good question, and we'll try and give you a simple answer. So the way to think about it is, when you think about a business process, or you think about an application process that you make in the form of a flow chart, so you make a diagram that shows how you get from one step to the next step, you can translate that into the form of a state machine. So a state machine is essentially a way of representing that flow chart of a workflow. And how you decide what goes in the boxes and what goes in the arrows is based on the notion of having statelessness between those states. So it's essentially the idea of passing around an email. And somebody writes an email and they press send. They've got no memory of what, they remember what they said, but they don't really worry about what they wrote in that email because it's been sent to somebody else to respond to. And someone else gets that email and they read it and they add something to it or they do something about it and they pass the email on to somebody else. So you can think about all those people as being, if you like, Lambda functions, passing this document between each other, doing things to that email, and then passing it forward, but then moving on to some other task they're worried about during the day. And so you make this flow chart. Each of those states does a piece of work. Sometimes that work is called a Lambda function. Sometimes that work is make a decision, like go to the left or go to the right. Sometimes that decision is take this work and divide it across three different paths and come back to me when all three are done, which is like delegating work to a group of people. And so you think about if you can describe your business process in the form of a workflow that you can visualize in the form of a flow chart, then your developers can turn it into a state machine, and then you can execute as many copies of those as you want using AWS Step Functions.
There was one really good question. Oh, it's on the screen. Can you dynamically invoke n lambda functions depending on the output? So, in fact, can you have a loop, really? So there's a bunch of ways you can do that. If you think about it, you can use a choice state, which depending on the input, loops back to the state before it. So you could execute a bunch of functions once after each other, or you could do them in parallel. So either of those is perfectly straightforward. Ernesto asks, I'm looking for a map rather than a choice. And yeah, that's a good idea. We're thinking about it. Somebody asked a question and went by asking, well, where's the state really stored? And the answer to that question is, well, we do it the same way that people who've been hand-rolling these things do. We store it in a database. And then the difference is that we offer that as a service, so you don't have to think about the database. What else? Is there a testing mocking framework? Unfortunately, the answer to that is not yet. And obviously, that's a good thing that we should all be thinking about.
Let's see. Let me see. So there's a question from Manish about does step functions handle passing the output of one function to another, or is that the Lambda author's responsibility?
No, all the Lambda's author's responsibility is to arrange for the proper output to come out of a Lambda. Then it's step functions' responsibility to ensure that gets handled as input to the next state. Ashraf asks, can you generate reports out of the state DB? Well, yes, but you're going to have to write the code. It's just a database. You can list all the executions, list all the functions, list all the steps of any.
This is all accessible through the API.
This is all accessible.
So this is where
the API.
So for example, what you would do to find the execution history of a particular state machine is you'd say describe execution history of state machine XYZ and give it the name of that execution, and what will come back is the complete audit trail of that execution.
There was a question earlier saying, what happens when there's an error in a Lambda function, or for that matter, an activity? And I think we showed you that there's a retry and there's catch and so on. But sometimes maybe that didn't work. Something happened that you totally didn't foresee, and you didn't have a retry or a catch. And if it blows up, then we fail the state machine execution, write a nice report into the audit trail, and pass it back to you. Okay, it looks like we got time for one more. You got one on mine, Andy?
Yeah, so Adam asked, is this meant primarily for machine workflow, or is it meant to be the next evolution of simple workflow? And I think the answer to that question is both. So our view is, for people that have used simple workflow and are getting good results with it, we encourage you to continue using it. We'll continue to support it. As Tim mentioned earlier, it's heavily used inside AWS and Amazon. It's going to continue to be available, and so there's no concerns. But on the other hand, we think AWS Step Functions is a lot easier to use for the same kind of applications as you might build a simple workflow and more. In fact, we think it's simple enough that you'd even contemplate using it instead of writing scripts. And so I think the short answer is we encourage you to try Step Functions in all the places you can think about using simple workflow and more.
So I guess that's about it. I guess we should say thank you. I mean, this has been great. This is so much more fun than giving a speech from a stage, having the live questions come in and being able to answer them. So thank you all for showing up and for all the smart questions.
Awesome. Thanks a lot. We will leave the room open for a few more minutes and answer any last questions that we can get to. If you haven't already taken a minute to reply to the polls you see on your screen, go ahead and click on the radio buttons, and then also give us any feedback in the poll down at the bottom. Really appreciate everyone taking time to join us today, and enjoy the rest of your day. Thank you.